All right, so I think we can get started. At least on my clock, it's 9:45 in the night. So if you're wondering who I am, I'm Jasper, or Jasper in German. Full name Jasper Bongertz. Some of you know me, and I've seen a couple of familiar faces or names on the chat list or the attendee list. If you're wondering why I'm not Hansang, it's simple because I'm not Hansang. Hansang is not able to do his talk for a specific reason, and I wish him well, but this is not the first time that I had to take over for him, and it worked out fine the last time, so let's see if it works out fine this time. I'm glad you're still here, and you're not moving away because I'm not Hansang, but well, I had to do something on a very short notice, and I wasn't going to present at SharkFest this time because I was helping organize it, and well, I can jump in, so that's what I did. And I had to choose a title, which is Packets Wait What. I stole that from Gerald Combs. He made a sticker that is on my laptop. And this computer right now is not my laptop, so you can't see it, but I liked it, so I used it. And I have no idea what we're going to do, really. I just picked a couple of PCAP files, and we'll walk through them. And I hope you find it interesting. I think there are some things in there that may be new to you or maybe not, and some may seem familiar because I know a few of you have been in my talks in the past, but maybe you've already forgotten about them because that's what we usually do, we forget about them. Okay, so let's get started. About me, I'm now working for a company in Germany that is called G-Data Advanced Analytics. My main role is doing incident response and network forensics. And my Wireshark community things are mostly my blog, which I haven't written a lot on in the past year for various reasons, mostly too much work. On Twitter, I'm PacketJ, and of course, I'm at SharkFest, obviously. I also wrote a little tool called Trace Wrangler, and if you ever have the need to sanitize a PCAP file or remove sensitive information from one, you might want to check it out. It's easy to find. If you just Google for Trace Wrangler, you will find it. So let's see. Well, I don't have many slides. People who have seen my talks before know that I very often only have like 3 or 4 or 5. This is a 4-slide talk, I think. Yep. So what we're going to do is just go into the PCAPs and have some fun with them and see how far we can go, because I wasn't sure how much time I can spend on all of them, and we will just go through one after the other and walk through them. All right, so let's do the first one. And while I open this one, there's a question from Arthur asking about any experience regarding packet brokers. And I have to admit, I don't have much experience with packet brokers because they're quite expensive, and usually I have to buy all my capture equipment myself, and I can spend like a 5-digit number on packet brokers. So I don't really know which one is the best, but I think if you're going to spend that much money, just get one that you can test before you really have to buy it. That would be my way of doing things. Okay, so I hope you can see my screen with the PCAP file, and I will increase the font a little bit. So this is my first case, and it's pretty short because I like my traces to be short so that I can walk through them without having to show you like scrolling pages all the time. In this case, this works sometimes if I have larger PCAPs, or if I do presentations on larger ones, of course, then we do this. But this is a very simple one. And some of you may be wondering why I'm having the default profile loaded, because usually everybody has a modified profile. There's a specific reason for that, because I just want to guide you through the changes that I usually do for my Wireshark analysis. I don't really like the colors in the background, so I usually change them. But in this case, let's just go with them. The other thing that I don't like is the time column. The time column on the left here shows me the time from the beginning of the PCAP file. It starts with 0, of course, and then goes up as much as the packets come in. Usually I would love to, or prefer to, have something called like a delta time, so the time between packets. But I think we can begin with just this column setup. As you can see, there's a Syn packet, and Syn packets are the ones that start a TCP connection, as most of you probably know. The interesting thing is that there is a retransmission of the Syn after 3 seconds. And if you look at the time that it took from the Syn to the retransmitted Syn, it's like so close to 3 seconds that I would say, okay, there's something not coming back to the node sending the Syn. And we're probably on the client. We can tell that from timings, which is really hard to do if you're just having the relative time column. But if you do delta times, we can do that pretty quickly. So let's just add the delta time. If I go into any frame down here, you will see there's a lot of different numbers. Delta from previous captured frame. This one is usually not that useful, because if you're applying a filter and filter away captured frames, the times that you see will be between now hidden frames and visible frames sometimes, and throwing you off. So the good one is to use the time delta from previous displayed frame. I want to have that as a column. So one neat trick that you can do now, since version 3 point something, you can just click on it, hold down the mouse button, and pull it up here to add it as a column. And what I usually do is, because the text of the column is too long, I edit the column and say, let's say delta time, like this. And often I'm also annoyed by where the numbers are, so I align them in the center. So this is much better. So you can see we're sending the Syn. We're sending a Syn again after almost 3 seconds. And if you see these 3 seconds as a network analyst, you usually know that that means there's some kind of timeout, probably. It's too nice a number to be by chance or something. So that is just a retransmission that was triggered because there was no Syn ACK coming back. So if you're seeing this, immediately you know there's some kind of trouble with the TCP connection, because the Syn, the first one in frame number 1, didn't get through. So the second one does, apparently, because after only 2 milliseconds, 0 seconds, 002 milliseconds, and then 56 microseconds, after 2 milliseconds, we get a Syn ACK back. And then we finally can complete the handshake in the 4th packet by sending our final ACK. And from the timings, you can tell that this one here is 18 microseconds. So if we're looking at the timings, we know that we are sending the Syn. The Syn ACK is coming in from the outside world somewhere. And then we're sending our ACK really quickly, which means we're very close to the TCP client. And I call it TCP client because it could be a server connecting back to a client if there's, for example, a FTP connection. And in this case, it's important to say, well, the 192.168.0.1 is the client from the TCP connection perspective. It's sending the Syn and it's sending the ACK. So we know we're pretty close to that one. And then after this problem with the connection already happened, and we know that somehow the Syn ACK didn't get back to us. We don't know why. Maybe the Syn didn't make it through. maybe the SYNAC didn't get back to us, it was lost somewhere. So, or the server on the other side was so busy at that time that he didn't reply with the SYNAC. And if we take a look at the 5th packet, there's another black marked line called TCP0 window. And a TCP0 window is something where we usually get nervous, because TCP0 window, as most of you probably know, means that this IP address, or the stack on this side with this IP address 192.168.0.101, tells us, hey, sorry, don't send me anything. I can't receive anything right now. And that is really strange, because we didn't do anything yet except creating a TCP connection. And right away, this guy is telling us, hey, don't send me anything. That usually shouldn't happen. And then after that, we can see there's a TCP window update. And the TCP window update means that the node now tells us, hey, now I can receive something. And it tells us, well, it's 2048 bytes. That is not a lot, but well, at least it is one packet. So in this case, if I see something like this, I know right away that there must be some sort of trouble on this device, because first of all, the handshake takes way too long. And you can see that by also looking at the transmission control protocol down here. If you go down to the sequence analysis, oh, this one tells us it's 2 milliseconds, which is kind of, we could argue about this one, because 2 milliseconds would mean it's from this SYN. Let's set a time reference to see how long it took to the ACK. So this is this time, you can see here. Let me just try to mark it. This, oh, no, it's the wrong key. I need a box. How do I make a box? I make a box with this one. So this here is this. And if you're honest, we should have calculated from the first SYN, because the second SYN is already a retransmission. So the original connection started here, not here. So from my point of view, this IRTT, the initial round trip time that Wireshark calculates, is a bit of a lie, because it should have been more like 3 seconds, not 2 milliseconds, because that is just if you're ignoring that there has been a retransmission. So sometimes you need to double check what Wireshark is telling you. And what I often do is, when I see something like this, I start reading the source code of Wireshark to find out why it does what it does. I won't do this right here. I think I have done that in a couple of talks that I've done in previous times. But it's just that in this case, the code determined to be the initial round trip time. And I think that's not entirely correct. So, oh, no, I don't want to zoom. Go away. Okay, so it's a weird little trace, because there's not much happening. And if you can see how long it takes in total to run, and if I can unset the time reference, you will see it takes 4.3 seconds for these couple of packets, 4.3 seconds for these couple of packets. That is just not really, I mean, that is really a bad time. So something here is really slow. And if we're asking the question, who is slow? Well, obviously it's this one on this side, because it's also with the 0 window, it takes 1.3 seconds to recover from this, and we didn't even do anything. So I would investigate what this server 192.168.0.101 is doing, because that is not a fast connection. Okay, let's maybe move over to my own profile in case you're haven't created any profiles. From the default profile that looks like this is how it would look like with my profile, my standard one. I have a couple of other profiles. For example, one that is just showing me layer 4 that looks quite similar, but I use that a lot if I have like HTTP GETs in there and I want to see the sequence numbers. For that kind of thing, it's pretty useful. And you can also see that I changed my layout so that I have the decode on the lower left, the hex bytes in the lower right corner, and a full height packet list, or more, not full height, but a higher packet list, more space for it. Right now I'm presenting on a full HD monitor. This is usually a 4K monitor, which would be giving me much more space, but for this Zoom session I felt it better to go down to full HD and not have tiny characters on the screen. So let me just check the questions real quick, because well, will PCAP be shared? I have to check. I can probably share some of them if you want me to, because they should be shareable. There's nothing special in there. If I may have to check one of them or two of them before I can do that. So if you want me to, I will just share them and upload them to a retrospective page later. So then Gregor is asking, how do we know that frame 3 is ACK to frame 2 and not delayed ACK to frame 1? That is a pretty good question. So the frame 3 is this one. How do we know it's, yeah, well, you're right. It could be like a very delayed ACK to frame 1, but 3 seconds is not very likely. In my experience, if we send the Syn and then the other guy on the other side takes 3 seconds to react to it, that is eternity in a network. So I'm not sure if that would happen. Most stacks would have probably dropped the packet by then. I think it's much more plausible that the second Syn made it through and got acknowledged. And we don't even know, because we don't have the capture on the server side, if the first Syn made it even through. It's possible that it never got to the server. That's also a possibility. And you can only tell if you're capturing on both sides at the same time. If you don't do that, it's a little bit of guesswork. So right now, my guesswork is the first Syn didn't get there, and the second Syn did, or the first Syn did get there, but was discarded because the server was so busy, and then the second hit it at a better spot or at a better time and got answered. So, and then I think we can assume that the Syn ACK is the reaction to packet number 2 and not packet number 1. So let's see what Wireshark thinks. Well, Wireshark, you can see the little check mark up here. This one, that tells us that it thinks it's the Syn ACK to the first packet, which is kind of funny, because if we're looking at the initial round trip time, it tells us that it used the second Syn for this. So there's code in Wireshark that tells us the Syn ACK is for the first packet, and there's code in Wireshark that tells us it's for the second packet. So that's a little strange. And I promised in my short description we will see a couple of strange things in these traces. Sometimes because Wireshark is written in a way that it is. Okay, so that was answered live. That also, packet 2 shouldn't be retransmission. Yeah, there's another question. Should it be retransmitted after retransmission timeout, RTO, which would be around only 100ths of milliseconds? Yes, that's possible too. So the Syn here retransmitted after 3 seconds, we could have seen it faster, because RTO, retransmission timeout, which is the time a node waits before it resends a packet again if it doesn't hear anything, is often like 100 or 200 milliseconds. But that is different for connection establishments. Very often stacks wait longer and use different times or RTOs for the Syn repeated than they do if the connection is already established. So it depends on the stack. It would be possible for the Syn to reappear faster, the retransmitted one. It could also be, like in this case, only after 3 seconds. All right, what else do we have? a SYN-ACK coming back with a window of 0. Yeah, that's also fun because the server tells us in the SYN-ACK already that there's a 0 window. Sometimes you see this, but it doesn't really matter at that point. Or does it? Well, let me think. I've worked a full day already, so I'm a little bit tired, and sometimes my answers I may have to think about things myself a little bit. So you're watching me analyzing this live, actually. And I haven't seen these traces in ages, so I'm surprised by some of the things that you find in there, just like you are. So yeah, there's a 0 window here, but it's not marked as one because probably if we look at the code, the dissector is not marking packets with a SYN flag as 0 windows. Yeah, actually that would mean that it can't even send anything else. Yeah, it's quite interesting. It just means that this stack is doing something really fishy, and I would investigate really closer to the server what is going on. Maybe even a device in the middle is changing things, but I think we don't have anything between the two. Let me just check. Okay, we see that the client has a TTL of 128, so that is a normal starting TTL for Windows. And the server is coming back with a 64. 64 is a normal starting time of Linux and FreeBSD and others. So it looks like that there's no hops between the two. And also these two IP addresses look suspiciously like they're in the same subnet. They probably are in the /24 subnet. So there's nothing between them that could change any content of the packets. So I think, yeah, this is actually something where I would try to find out what the server is doing. It's really a strange little trace. All right. Oh, Sake is here as well. Now I need to be really careful because Sake is much better at TCP sometimes than I am. He asked, Jasper, why are there MSS options in non-SYN packets? There are MSS options in non-SYN packets. That is true. Yeah, interesting. Haven't seen that. MSS should only be, or usually you only see the MSS in SYN packets, but those two have them. This is a weird TCP stack, and I'm not sure where this trace comes from. And it's from 2013, as you can see from the timestamp here. This is really weird. So at least I kept my promise. The traces are weird. If it's only this one, but I have no idea why there's a MSS in that packet. I have no idea. Okay, so the next one is, do you share any of your custom profiles, maybe on your website? Well, I can share them if you want to. It's usually better if you build your own, if you know what you need. There's also one page that I keep forgetting where it is. It is somewhere where a lot of profiles are shared. I think I can put my profile on the retrospective page if you want me to. That's not a problem. So, SYN retransmissions will have a different IP ID. Let's check if it has a different IP ID. Chris Hull says. So the IP ID here is 52092. And this one is 52123. So this is a retransmission. It's not a duplicate. It's a true retransmission. Okay, is the relative time since the beginning of capture? Is a question asked by Patrick. Yes, it is. The relative time is starting at the beginning of the capture, except if you want it to be from a different starting point. That's what I used for a while. And let me just go back to the default profile so that I don't confuse you that much. You can see here that the relative time, and we can rename it so that we can tell relative time. The relative time is counting up like a stopwatch from the first packet, which is why the first packet has 0. And then the time goes up by the delta time. So the second packets arrived after almost 3 seconds. Then it took 2 milliseconds, and this will be added accumulatively to the relative time. But if you want to, and you want to know, for example, how long does it take from the 0 window to the window update, well, that is easy because it's in the delta time. But let's say you want to know how long does it take from the 0 window to the, I don't know, let's say to the 7th packet, like the push ACK, then you just go into the pop-up menu and say set unset time reference, and that will force a new 0 on the relative time, and it will mark it as ref, which means reference point. And then you can see it starts from 0 again here, which means that these two numbers are the same. So the relative time is from the beginning of capture, unless you're putting in there some reference points, then you will force it to reset. That only affects the relative time, not the delta time. Okay, so that is important. And you can always unset it again with Control T, which is quite useful. All right, so, oh, Manfred just put in here the HTTPS wiresharkprofiles.com. Let's see. There are profiles. Oh, there's Betty's. And I'm not sure how many else there are, but I think I uploaded mine to some page at some point. So yeah, there are web pages too where you can download profiles. All right, so more profiles. Oh, the Cellstream one, yeah, that's the one that I forgot about. That's the one where I uploaded mine at some point, but it keeps changing all the time. So yeah, you have to basically build your own profile. That's what Chris Greer always says. He can show you yours, and I can show you mine, but you need to combine whatever you need for your analysis, basically. So get some ideas, go get them, find out what is happening, and see if they're useful for you, and then build your own. That's what I do. Okay, so that's all the answers that I had to do for this one. So let's go to the next one. Okay, so this is a fun one. It's a small one again. There's an ARP request. And then we see, once again, a Syn ACK. And then there's a Syn again. And after the Syn, there's a reset. So, this is really strange because, I mean, there's a Syn, and we're probably once again close to the client. I don't know. We're once again in the same subnet, probably. Let's check it out. We're time to live 128 for the client, and we're at 32 for the server. That is a weird one, but it looks like it's a good number to the power of 2. Is it 2? 2x to the power of 6, or I'm bad at math, so forget it. It looks like a good binary number, so I think it's also a starting hop count or a starting TTL, so there's probably nothing between the two. Also, we have the ARP requests, and we could check if the MAC addresses are the same, because if the MAC that answers is also the one that is used here, and I think it is, yeah, the F387 is this one, the 59 is mine. So from the ARP request and the ARP response, we can also tell that both IP addresses must be on the same subnet, because otherwise they wouldn't be able to ARP each other. Well, the client could ARP for it, for the server, but it wouldn't get any answer unless the server is on the same subnet. So these two are in the same subnet. There's a Syn, there's a Syn ACK. I think I left the ARP requests in there because it will give you the hint that there's nothing between the two. And that means that when the Syn ACK comes back and we start with a Syn again, there must be a reason why we're sending the Syn again, and after almost 3 seconds again. So that is kind of interesting. So what is happening here? Right now, I can't see anything special why it wouldn't work. So let's for a moment assume that the SYN is okay, because I mean the SYN was sent, the SYN is sent again. There must be something with the SYN ACK. The question is, what is going on with the SYN ACK? So let's check. Nothing to see here, but one of the things that I usually do when there's nothing really obvious going wrong is to check if my Wireshark settings are as I want them to be. And sometimes they're not. I can see, for example, that header checksum here for IP is disabled. And very often I want to know if the checksum is correct or not. So let's just enable this one. You can do that really quickly by selecting the protocol header for this section. As you can see, this is the header for this IPv4 section. Right-click and then go to Protocol Preferences, and here you have the options of this protocol. It's much faster than going to the Edit Preferences section. So let's validate it, and we will see that the checksum here is correct. Let's see what happens with TCP. It's also not verified. Okay, so enable that one as well. By the way, it says validate the TCP checksum if possible. The if possible means sometimes it's not possible to validate the TCP checksum. The question is, when is it not possible to validate the TCP checksum? And the answer is relatively simple. If you cut away the payload for various reasons, like if you're not capturing the full packets, then the payload is missing. And usually what happens is you can't calculate the checksum. So that's why it says if possible. Okay, let's enable this. And what we have here is, oh, look, the checksum is incorrect. It should be XDCF3, but it is XDCF4. And then there's a text saying maybe caused by TCP checksum offload. Well, it could be, but if you take a look at the checksums, and I think we can even open it up like this. No, it doesn't say much more. When I see a checksum error like this, where the number that it should be is very close to the one that you find, I mean, DCF4 instead of DCF3, that is just 1 bit basically that is missing. And it's very likely that this checksum is caused to be wrong by just 1 bit flip at some point. So it looks like that in this case, actually, there is a checksum error because something in the packet broke during transmission. And that is the reason why after sending the SYN and receiving the SYN ACK is discarded. Because if the checksum is not correct, well, the TCP stack won't accept the packet. And in this case, if it's not accepted, it will send it again. It will send another SYN and try to connect. And then it's really strange because we get a reset back. But once again, the checksum is bad and it's once again off by 1, apparently. So this is another very strange trace because 2 times the checksums are off by 1. And also, if we're looking at the TTL of this guy, it's 32, and that is also a strange number. Usually you see 64, 128, and 255. Seeing 32 usually gives me the impression that somebody is maybe programming his own TCP stack, or it's some experimental thing, or something that is not really well tested. So in this case, I'd say, well, this stack does something fishy, and I would try to find out what is going on, and once again investigate the server on this side. All right, so let's see if there's more questions. I need to scroll here. How likely is it to have IP packet damage while Ethernet FCS is valid? Good question, because if the TCP checksum is wrong, usually the Ethernet checksum must be wrong too. That's not the case here. Because why do I know that the Ethernet checksum was correct? The simple reason, or the simple answer to that, is because the packet is in my PCAP. If the Ethernet checksum is really damaged, broken, kaput, that would mean that the network card that I'm capturing on would not accept it. Damaged FCS frame check sequences mean that the packet is discarded, but it ended up in my PCAP not just once, but twice. So it looks like that maybe this error of the checksum, or the reason that causes TCP to have a bad checksum, is actually maybe even in the code of the TCP stack that's sending these packets. So that is a pretty good question. So it's not very likely to have a TCP checksum error and not also a broken Ethernet checksum. So the packet should have been discarded usually, but in this case, it's not. Okay, would this scenario be indicative of a potential SYN flood attack? I don't know if you have, okay, SYN flood means somebody's sending a lot of SYNs. And in this case, these are not enough SYNs. If you have ever seen a SYN flood attack, and I've seen a couple, you get line saturation with SYN packets, which means you see millions of them in mere seconds. This is probably not a SYN flood attack, especially since both nodes are on the same subnet. And SYN floods usually happen, at least these days, from coming in from the internet from a lot of different nodes. So I don't think we would be calling this a SYN flood thing. It's not very likely. Okay, you have VSS payload at the end. Should you change Ethernet protocol settings? I do. Okay, let me check. Yeah, VSS monitoring Ethernet trailer. Some of you may have seen this kind of thing. I'm not really sure, but I think I can blame Sake for this, because it basically means that after the TCP protocol, if I click on the protocol, as you can see at the hex bytes down there, you can see how the bits, the marks tell me what is in the packet. So the last one has it. And if there's trailing bytes after the packet is complete, then there's some code in Wireshark that tries to detect VSS monitoring Ethernet trailer. I think that is something that is added by some tabs built by VSS, by the vendor VSS. And I think Sake put in the code for this. So you can disable that if you want to. I think on the Ethernet settings, I rarely do that kind of thing. Or maybe it's even here. Let me check. You could disable this and then it's gone. Usually I just don't care. If I see a VSS header down there, I'm like, okay, there's some trailing bytes, and just be okay with it. It depends. If it's annoying for you, you could disable it. By the way, if I want to enable it again, now I can't do the trick with the right click anymore because this line is gone. So now I would have to go into edit preferences, protocols, VSS something. Where is it? I don't know where it is. Maybe it's, I have to check. It's an Ethernet maybe. No, I don't know. I don't care. And especially it's a default profile. I don't know. I don't need to use it anyway. So it's because there's some trailing bytes after the packet content. Isn't the checksum actually off by a 3-bit flips? Oh, now you guys are now calculating how many bit flips there are. I'm not awake enough to do that, so probably you're right. And I'm pretty bad at math, so there's something wrong with these packets, and it's interesting that they're both wrong and off by 1. So you're probably right. They're probably off by a 3-bit flip, but I I'm too tired to calculate it right now. It's too late in the night for me. Thanks, Stefan. Good catch. Wes Morgan. I often see TCP checksum embedded on packets I'm sending because, yeah. Wes Morgan says you're often seeing this TCP checksum incorrect on packets that you're sending out. That is because you're capturing on the local computer and the packet is not completely commissioned for the network yet. So the checksum has not been calculated. That is also the answer to any of you who are wondering why Wireshark in default doesn't check checksums. That is because too often people capture on computers sending the data and get confused by seeing checksum errors. These are caused by the method of capture and not because they're really broken. Thanks, Wes. So Vladimir, FCS is calculated down the stack. I didn't think it. Okay, Vladimir, he's way too much ahead of me talking about this kind of thing. So yeah, you're probably right, Vladimir. Good, I have more traces. How much time do I have? I have, I think, 20 minutes left. Let's do another one. Okay, so let's check out this one. So Syn Packet, this looks great. Nothing special. Nothing special. So scrolling. Ah, there's something. All right. 4 packets with colors, and for this kind of thing, this bar here is quite nice because you can see right away where the colors are different. So there's something going on here. Dupex. There's something going on here. Well, let's check it out. So what do we have here? We have a connection that is finished, and then there's a new one started. Let's check first if this is really a new connection, because you can tell quite often if this is a new connection or not. And what I do to find out if a connection really ended at that point is I use the right mouse click, colorize conversation, TCP, because I want to know if this TCP session is complete. And then I just select any of the colors. And as you can see, this is really weird now because the packets seem to change. What did I do now? Okay, I tricked myself somehow. Dupex. Ports reused. This is kind of strange. But I was promising you strange traces, because usually if a new connection starts, you get a new color. But let's try something else. The colorization doesn't work. Let's just see if we can tell by the TCP stream index if there's a new connection. TCP stream index 0. We can just put that up here as a column 2. Now we can see there's one stream ending, the number 0. Then there's a new one starting here with a SYN, and it says TCP port numbers reused. That is a diagnosis made by Wireshark telling us that the exact same IP addresses for the client and the server, or source and destination in this case, and also for the ports from the client and the servers are identical. So we can see here, yes, the old connection was 43 and 24,426, and the new one is using the exact same port numbers, which is a little bit too soon, because usually you should wait quite some time before you start reusing ports. In this case, they only waited 16 seconds, which is great, once again, to have the delta time so that you can see how long did it really take. And 16 seconds is too fast to reuse the port normally for it to be safe. So what happens here is apparently they want to do another connection. The same port is used. Then we see that there's a acknowledge coming back, and it's TCP ACK unseen segment. So this is really getting strange now, because there's an ACK that is so high that it can't be for this packet, because we would expect to see an ACK of 1, but maybe that is caused by some strange relative sequence number setting. So let's just check out what the absolute sequence numbers are. Now the numbers get really big and it gets annoying to work with them. So this is a sequence number from 192.168. It had used 24.3 something, and the Syn uses 22 something. That is really far apart between these two. If you take a look at these two, the box was what? Control. Okay, this one here and this one here, they're very far apart, and they're coming from the same system, if I'm not completely mistaken. Yes, it's both from 192.168.0.1. So this is a new connection, but it's kind of weird because the sequence number is lower than before. So I think what happens here is that the other side is still thinking it's the old connection, because we can see that his sequence and ACK numbers here, these two, I hope you can see my mouse pointer. If not, I will make some boxes again. These sequence and ACK number here are very similar to these two. We can say they're identical. So basically, we can assume that this packet that is the answer or coming in for the Syn is actually one of the old connections, and the stream index also tells us that this is the old connection. That is kind of strange. Why is it happening? I have to check if I'm clicking on the right packet. No, it's stream index 1. So Wireshark thinks the ACK here in 1045 is ACKing the Syn, but we can tell from the sequence numbers that it's from the old connection with stream index 0. So once again, the stream index, or the value that Wireshark gives us, is not correct. And then there's a reset, and the reset is happening because the port was reused too fast, and this node sees that the sequence number is so far out of range what it expects that it aborts the connection. So it starts using the same ports again, gets back an ACK that is for the old connection, which is so unexpected that it sends a reset to shut down the connection. And the interesting thing that happens now, it is starting once again the same connection, once again with the same port numbers. It's once again a TCP port numbers reused, but this time it works. So for me, the question would be, why does it work? Doesn't it work the first time? And why does it work the second time? So, well, the answer is because of the reset. The reset packet forces the sender and the receiver to discard the whole connection. Before that, the connection here, the old one, the good one that we saw running for quite some time, it was finished with a fin ACK, a graceful handshake at the end. And that means that the session state stays in the table for the stack for quite some time in this time wait state. You've probably seen that every once in a while. And this time wait state takes a couple of minutes, I think 2 minutes if I'm not completely mistaken. And if a Syn arrives in that time, that's why it answered with the old sequence numbers, because it still had the connection in the time wait state. As soon as the reset arrives, the time wait state is cleared and the whole connection is discarded. And that is why after 25 seconds, the port reuse works. And then they can transfer data. So that is just a very interesting thing happening here. The Syn coming in, hitting a old connection still in time wait state. Time wait meaning that the old connection is using the old sequence numbers and acknowledgement numbers, sending them out, and that causes a reset. That clears the time wait state, and then reusing the port numbers is possible. So from that we can take, if you're resetting a connection, you can reuse port numbers faster than if you are going to be the good guy and using fin-ag. So being the bad guy gets you port reuse, while the other way around wouldn't. Okay, let's check questions again. Check the sequence of the first fin. Sequence of the first fin. Yeah, it appears to be a duplex for line 2043. This one and this one. Yeah, okay. So I don't know why I would check the sequence of the first fin. I'm too tired to probably understand what you're pointing at, Manfred, so forgive me if I don't waste some time on this or spend more time on it. Wasting would be too hard. I think we just go to the next one unless there's more questions. Rob has a quick UI question. Sometimes I find the IP address in source and destination hard to follow. Is there a quick way to replace them with name I'm browsing? Yes, you can do that. There is, what you could do is, let's see if that works. Usually when I do something like this, it won't work right away. There's name resolution that you can use. You can enable this here in the view menu, go to name resolution and resolve network addresses. And if there's a DNS or if there are DNS packets in your trace, it will pull the names from the DNS. But you can also go and say, edit resolved name. And if you do that, it was maybe a bit too quick. You click on the IP address, right click, and then say add a resolved name, and I can say this is my client. And then I can click on this IP and say add resolved name, this is my server. And I hope that's what you're looking for. I think you need to enable network name resolution. Let's just check if I turn it off again, if it still works. No, because then it doesn't. So you need to enable the network name resolution, and then you can edit the IP addresses if you want to. Okay, Manfred, then he just told me that I already explained what he was pointing at, so I'm glad. Thank you. Okay, good. We still have some time. It's not a lot of time, but we have some time. So let's see the fourth one. Oh, that is a fun one. It asked me if I want to save something, probably because I edited the names. I think it wants to save the names with the file. Funny thing, I opened a new trace file and there's the same IP address in there apparently, and it keeps the name. So let's just turn off the, or well, we can just edit this one and say server, client server, client server. Nice. Okay, once again, we can see from the colors down here, there's something interesting. Okay, so let's remove this column. And I don't think I need the relative time. You can just disable columns if you want to hide them and not completely remove them. You can just click on them and then they don't have a check mark. So you can add them and remove them if you want to. So let's see what's going on. The server tells the client that the previous segment was not captured, which means there is apparently some kind of packet loss. Because if we're tracking sequence numbers, and let me just re-enable the relative sequence numbers because they're just too hard to read otherwise. Okay, let's see, what do we have here? We have the sequence number, server, the client is sending something, the server is sending something. And now let's just switch over to my profile because it's really hard to read this whole thing. This is much better. But now the names are gone. Anyway, Okay, so previous segments on catchers, we see sequence number is 10,944. We expected to see something else. Let's just check what it is. The previous packet that was sent has the sequence number of 8,209. The next one should have been 9577. 9577 is the one that should have been sent by this one, but it sent 10,945. So this is too high, which means Wireshark tells us, hey, there's a gap. I wanted, what was it, 9577, but I got 10945. So previous segment on catch-up means something is missing in the correct order of packets. Then we see dubak, which tells us, yes, this guy wants 9577. But the other guy sends 12.3.13, which is not marked as previous segment not captured, so it's probably correctly following the previous one. Let's check. This one here needs to be followed by 12.3.13. 12.3.13 is coming in, so that works. Then the other guy says, hey, wait a second, it's nice that you're sending me this, but I still want 9577. And it's probably also telling us somewhere down here that it got the other things here. In the sec block, it tells us, hey, I need it from 9577. That is what the X tell us. But the sec box tells us, hey, I got the other stuff that you already sent. I will keep it. And then there's a fast retransmission finally sending us the one that we needed. So everything is fine after that one. But, and that is the interesting thing is, it says it's a fast retransmission. So is it really a fast retransmission? Well, fast retransmissions usually are triggered by 3 duplicate X. But if you're really into Wireshark and you know how the code is written, it will mark something as a fast retransmission after having seen 2 duplicate X. The reason for that is that the programmers think that sometimes one of the duplicate X may get lost, so they mark a fast retransmission when they see 2 duplicate X, while the RFC, as far as I remember, says it needs to be 3. And also we can argue about, is a duplicate X number 1 not the egg number 2, because there's an original, there's a first duplicate and a second duplicate, so it gets a little hazy here. Let's just say that the Wireshark code thinks this is a fast retransmission because there had been 2 duplicate X, but is it really a fast retransmission? That is my question. And for that, we need to look at, well, how fast does it arrive after the location where it was missing? Usually when the packet is lost, the packet needs to travel from one side to the other, and then the lost signal, which in this case is the duplicate egg, needs to get back to the sender, and then the sender needs to send the packet again. So we have round trip time to even know that the packet is missing, and then half a round trip time for the retransmission to arrive. And let's just check how fast the retransmission arrived. And we can do that by, for example, marking once again with a time reference our packet where something got lost. Now my time columns are on the right, which is, which is something that I usually do, and Hansang gives me some trouble about. But for me, it works. So these are my time columns. We can see here that the fast retransmission arrived after 236 microseconds. That is pretty fast. So the question is that 1.5 times the round trip? Well, let's just check what the round trip is. The round trip is almost 103 milliseconds. We can check that real quick here. There's the Syn Packet. The round trip time is 103 milliseconds. And the retransmission arrived after 236 microseconds. So if you're sitting in front of your screen right now and you're saying this is never a fast retransmission, congratulations, this isn't a fast retransmission. It's just an out-of-order packet arrival. So this packet got switched in transmission. It just arrived after the 2 it should have arrived before. This is not a fast retransmission. This is actually one of the times that Wireshark is not diagnosing something correctly. And sometimes this happens. This is why you may need to check, is it really true or isn't it true? And in this case, this is not a fast retransmission. Wireshark is not telling the truth, so to speak, and we're working on that. So working on that meaning we're trying to fix the TCP dissector all the time and get things done. So I think if we're looking at the questions, we have one question left, or it's more like a comment from Chris. I've seen some TCP implementation retransmission only after 2 dubs, 3 of the same X. Yeah, sometimes the RFCs are looked after or implemented. Sometimes people implemented them a little different. It depends on the stack quite a lot of time. So if I'm not totally mistaken, I have used all of my 60 minutes to go through traces. I will try to sanitize them in case I need to and upload them so that you can download them later and check them out yourself. I will see if I can put in some additional context for them to yeah, add some more hints or maybe something. And thank you for watching. I hope it was interesting enough for you not to miss Hansang too much. And I hope you will be back. And thank you so much. And I'm done.